Okay, so good morning once again, everyone. In our first session today, Milan Toth will tell us why don't we actually need an LLM. So the stage is yours.
Thank you very much. So, hello guys. My name is Milan, and I came here today to give a little bit of provocative session why we actually don't need LLM and what we can use instead during our day-to-day operations, or not even during day-to-day, but for 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 actually four very kind of distinguished operations that we do. Um, with our platforms or with our clusters. So, quick disclaimer: this is not an anti-AI talk, right? I like to talk engineering, and I'd like this to be a pro-engineering talk, right? So, and instead of focusing on tools, I'd like to talk about principles. So, um, yeah, we've seen it all. Many vendors shipping new dashboards and new features with a lot of AI buzzwords and whatnot. So I believe the mathematics underneath should be more or could be more powerful and more effective than using or throwing LLM into our Kubernetes operations. So we have 35 minutes. So let's go. As I said, these kind of things like anomaly detection, capacity planning, and root cause analysis, failure prediction can be solved with mathematical principles or formulas, and they have been defined by math for a very long time. I believe using a deterministic approach to deterministic problem is much more effective than using LLM, which is probabilistic, and it's cheaper, right? It's actually auditable, right? And it doesn't lock you into any vendor. So as I said at the beginning, four problems, four areas that I would like to focus this talk on. How big should the cluster be? Any metric, is it weird or it's just the Tuesday? What can break next and why it broke at 3 a.m., right? When we all rather sleep. Yeah, AI theater. Why AI theater? I believe everybody is kind of now with the AI on a gold rush, and I believe it's important to stick to principles and why we actually don't need GPU for everything. So first problem, how big the cluster should be and what we actually can apply to identify the right size, right, for the right sizing. First thing, queuing theory, which was first not invented but described by Danish engineer Mr. Erlang in 1909, when he was trying to figure out how many phone lines Copenhagen needed, so he invented the mathematics. And now we use it in telecoms, in call centers, we use it in hospitals, even CPU schedulers use it. So, and Kubernetes pod handling requests is a queue as well. So we already know how to size queues exactly. Another mathematical formula called little law, where L equals lambda W, is the average number of items in a system, which equals the arrival rate times the average time spent there. So this is an identity. It holds in a steady state for any queuing discipline, and it's the one formula that I kind of become very fond of. There's a caveat to this. Little law is descriptive, not prescriptive. It tells you what L must be, does not tell you how many replicas to run. L is concurrent in-flight requests, not replicas count. And W is the mean latency, not your P99. So it's actually a hook, but the actual sizing, a peak replica count where the weight probability drops below your target is the Erlang C formula. That's going to be on the next slide. And we still don't need GPU. We don't need training data. We don't need anybody. We can do this by ourselves. Yeah, couple 100 lines of Python sits between your metrics and your horizontal pod autoscaler. Here what it looks here here's what it looks like in practice. You scrape two things from Prometheus, request rate and mean service time, and both are already exported by every sensible service, right? So you already have those metrics. You feed them through the Erlang C formula on an MCQ, and outcome is a recommended replica count. One unit note in case anyone is doing the math along with me. The scrape gives service times in seconds per request. The function takes mu as a rate. So invert it. So we invert it internally. So this is really rough formula. So it's not like you can copy and paste it, right? This is more kind of like a food for thought, and kind of like doing the exercise by ourselves somewhere when we have a free time. And this is supposed to serve as kind of inspiration. So this is actually the concrete example. This is the whole exporter, two functions. Erlang C gives you the weight probability for lambda, mu, and candidate replica count. Recommended underscore replica sweeps the replica counts until that probability drops below the target. So the return 256 at the end is a fallback. So if the system can't be sized with the cap, the gauge never goes to none. Wire this to Prometheus gauge, scrape lambda, and mean service time, invert the get mu. Now your horizontal pod autoscaler, your dashboard, your capacity meeting, all reading the same number, derived from the first principle, not vibes. This can be actually achieved in under 100 lines of Python code. This is those are my empirical numbers from my experience. Not many of us have the luxury to actually play with the clusters that, or where we can add the nodes based on some kind of autoscalers, right? So we often we play with the pods, right? Not with the nodes. We scale the pods, not with the nodes. I had the opportunity and luxury to work on some very big clusters in Europe, and those are my specific numbers. What I was able to achieve, not in terms of physical money saving, but if we would interpolate it into money, the ROI was this. This happened during the last couple of years. So the number is not really precise because the prices of the hardware kind of like fluctuates over the years of the time. So yeah, and really, I was running experiments on those clusters, and some savings were fictional because I wasn't really able to do the sizing of the cluster due to whether it was regulated environment, or there was no hardware spare to put into the cluster. Sorry. So another pillar of this talk about the metric that is going sideways somewhere. And for this, there was a method invented in 1924 called statistical process control by a gentleman called Walter Schubert at Bell Labs. He was trying to figure out when a manufacturing process was actually broken versus just noisy, right? So he invented control charts. Toyota uses them now. Pharmaceutical industry use it now. Semiconductors use it, so we can use them for the pod CPU as well. What's the principle? The control charts are simple. You compute the mean and standard deviation over stable window. Anything outside these three sigmas is an anomaly. The math gives you the false positive rate in closed form about 0.27%. One honest caveat, the exact number assumes Gaussian data. CPU isn't quite Gaussian. It's bounded, sometimes skewed, sometimes bimodal, so the real data drifts a bit. But for production system, also layer a multi-sampler rules and cooldowns to keep alert volumes same. But the point holds. You pick the false positive rates, you can defend it. Try to get this with LLM. False positive rates are bound and known. You pick the rate, you don't pay, right? This is the headline benefit. False positive rates are bounded and known. 3 sigmas gives you 0.27%. 2 sigmas gives you 4.55%. So if you compare this to AI anomaly detector, which doesn't use math, even if the AI anomaly detector would use the math, is actually anti-pattern to use LLM for mathematical and deterministic problems. So this is the whole alert in from QL, right? You take the CPU utilization, you compute a rolling mean and standard deviation over an hour. Alert when the current value drifts outside 3 sigmas. That's it. Again, this is not exact science what I'm presenting now, right? Rather, I would like to add some honest notes. First instance, the node CPU utilization ratio is recording rule you define from node CPU. Second, total. The existing stack doesn't ship a CPU usage gauge. You have to derive it. And the second, the offset 5 minutes on both recording rules is deliberate. It excludes the most recent samples from the baseline. So otherwise, a sharp anomaly pollutes the very mean and standard deviation it's being tested against. Again, you don't need any training data. You don't need any model. You don't need to call any API. So from day one, you can use this. Again, those are my numbers from my empirical my empirical samples. This is the the statistical process control conservatively recovers H2, or at least to me, it helped me 8 to 15 hours a month that I burned, on false positive pages. On a 10-person platform team, you can do the math. That's quite some time. So during a year. So another pillar that I would like to discuss is root cause analysis, the category where AI feels the most magical, right? And is actually the most dangerous. Many of you have been administering system where the spam detection was running, right? And we know this Bayesian networks since 1988, right? Mr. Pearl, he won a Turing Award for this. So what is Bayesian network? Oh, I will cite the literature. It's a directed acyclic graph. Each node is a variable, and each node carries a conditional probability given its parents. So when an incident fires, you run inference over the graph. Outcome is a ranked list of likely causes with probabilities attached, right? Again, you need a formula for this, or you need an algorithm to do this, but I believe if I was able to do it, anybody is able to implement Bayesian algorithm on their own. So here's the critical part. For any of us who had to do a post-incident review, every answer is auditable, right? You can trace exactly which edges fired, which priors moved, why one cost ranked above another. So I have used LLM to do a postmortem, these GPT models to do some root cause analysis. But sometimes the data are very sensitive. You don't have the luxury to use the LLM, or even the connection to the internet might not be available. So so only auditable and audited tools can be executed on the cluster itself. So yeah, this all comes together, into the stack, and how does it plug into a real stack? We all love OpenTelemetry, right? And OpenTelemetry traces gives you the service graph for free. So, two honest notes before you walk away. This is a plug and play. First, real service graphs have cycles, right? Shared services, callbacks, event-driven flows. Bayesian networks needs DAG, so you break the cycle first, you drop the weak edges, use the dynamic Bayesian network with the time index nodes. That's why the slide becomes the DAG, not is. Second, learning conditional probabilities from incident assumes you have labeled incidents. Many teams don't. So hand authoring works for small graphs. For large topologies, you want a hybrid. New incident comes in, you run inference, and you get wrong ranked causes. The graph is the explanation. Measurable. Mean time to recover. Teams that ships Bayesian root cause analysis on top of their open telemetry data typically cut mean time to resolution noticeably. The exact number depends on your incident base rate. So, but more importantly, every output is explainable, right? So you really are able to explain what have happened, and every output is auditable. Again, I came from work in regulated environments where you don't have the luxury to plug your MacBook into any tool you wish. So the fourth, the last pillar of this talk is what will break next, right? So what can actually break? So let's play this game of trying to find out what can happen. So this is the one the vendors are the most excited about right now, because AI can really predict, incidents, and AI can really do anomaly forecasting. And it has been solved deterministically. So in case you wish, you can look at it from another point of view. It's an entire field for this, and it's called survival analysis. So Mr. Weber in 1951, Kaplan and Mayer in 58, this is the math. Insurance actuaries use to price your life insurance. The aircraft maintenance crew used to decide which parts to replace next, and the cancer trials used to compare treatments. And critically is the math hard drive manufacturers have been using since the 90s to fit the smart data and predict disk failures. So we are not inventing anything, we are catching up. Throwing LLM to all these problems, you might be losing details, and you might give up some auditability. So here is the entire toolkit on one slide. It's the reliability function. It's probability that a component is still alive at its time t, right? So 2 parameters to fit. ETA is the characteristic life, the time scale of the system, and beta is the wear pattern. Less than 1 means infant mortality. Equal to 1 means memoryless random failure. Greater than 1 means wear out. So then you plug in t, how long the thing has been running, and 2 parameters, closed form, fit from your own incident history. That's your predictive maintenance system. Again, the math has been here for a long time, been using in a very, very critical parts of our lives and businesses that are fueling the economy, and it can be also applied to Kubernetes operations reliably. So how it actually plugs in, your cluster is already emitting everything you need. Certificate expiry, cert manager already publishes no after, predicts the storm before the page arrives to your phone. Again, some side notes on certificates. Strictly speaking, certification expiry isn't a survival problem, right? It's timer math. Not after isn't known exactly, but it feeds the same maintenance scheduler that consumes the Weibull and Cox outputs. So I'm bundling it here. Disks and PVCs, smart metrics, fit and variable replace the volume before it dies. So this applies to nodes, memory pressure trajectories. You can replace the node before it OMs. Again, you don't need model, you don't need GPU, you don't need API to call. A little comparison of the math versus LLM for these 4 problems side by side. Mathematical or math is cheap, it's auditable. It has bounded error, right? So we can really say how precise we are, and it runs on what you already have. LLMs are expensive per query, they have unbound error, right? They hallucinate and they need GPU and a lot of inference. So for these 4 problems, and I'm only talking about these 4, the math wins over the axis. That matters at least for me and my operations and what I do. I don't have the luxury to use LLM all the time, at least not outside my home. So, but for the work, I don't have the luxury to use the LLM. Again, this is not the anti-AI talk. Here is what I believe LLMs do earn their keep, like natural language interface to your cluster, right? Summarizing 1,000-line stack trace, drafting runbooks, reading and writing YAML files. And anywhere the input is language and the output is language, LLM is great. Just don't ask them to do the arithmetic. Cloud Native of the foundation stack ships the instrumentation. It leaves the math to vendors, right? So we have all we need. We have all the tooling. We just need to plug in a little bit of creativity inside to achieve the most precise results, because it's kind of not my hobby, but I believe the right sizing Kubernetes is a business problem. And right sizing Kubernetes determines whether your operation is economical or not. So Prometheus gives us metrics, Kira gives us auto-scaling triggers, Kubeflow gives us ML pipelines, and OpenTelemetry gives us traces. What none of them ships is capacity planning, statistically anomaly detection, failure prediction, or probabilistic root cause analysis. Yeah, you can use, for example, the horizontal pod autoscaler in recommendation modes and stuff like that. But the gap is there, and you can feel it. Approximately 200 line of math. You don't need any AI. 4 tools, they all read what you have. All write back what you already consume, right? The integration story is honestly boring, which is the point, right? Queuing theory exporter reads Prometheus, writes Prometheus, your HPA consumes it. Statistical process control alerts. Pure PromQL recording rules lives in your existing alert manager. Variable fit reads certification manager, smart metrics, not telemetry, writes a Prometheus gauge for your maintenance scheduler that reads it. And the Bayesian root cause analysis solution consumes the OpenTelemetry traces, expose an API. Your incident bot already knows how to call. 4 tools, no new infrastructure, no new vendor. That is the decision framework, how to decide, This is the part you can actually take home in 3 steps, and you can use it next time somebody pitches you an amazing tool. Classify the problem. Deterministic with closed form answer. Statistical with known distribution. Casual with known graph. This is what I did. I spent a week with the math. First, read couple books, couple papers, talked to my friends that are actually mathematicians, because I'm not a mathematician, I'm not a scientist. Reach for machine learning only when the input space is genuinely unstructured. Logs you've never seen, free text incidence reports. I have some toolkit available, but I'm not publishing it. If somebody is interested, I can, upon request, share. Caveats, because I'm engineer. Queuing theory assumes poison arrivals, usually true. Check yours. Statistical process control assumes a roughly stationary process. We have 5 minutes left, so I will speed up. Again, these are my numbers. Doesn't have to be yours. Just sharing what I've learned and what I've experienced. Those are the 4 names to remember. And I would like to end the presentation with one funny quote. I like to, beside computer engineering, work in a workshop, right? And between my friends, we have a note or a joke that the one who dies with the most tools wins, right? And I kind of find it funny to apply to the optimized cluster. So you can print it and stick it somewhere if you want. Thank you very much. I think they don't know. They simply don't know the tool they can use, because we are being bombarded with tools, right? It's tools epidemic and tools for everything, especially in the cloud native space. We have many tools, and it's kind of, to me at least, right? Not some Altman. I don't know. I don't know much about GPT, because I'm not an AI expert. Would be correct to say that Bayesian network with self-attention is GPT type of large language models? I don't know. I don't know anything. I don't know everything, right? So, is Bayesian RCA root cause analysis prone to survivorship bias? Maybe yes, maybe no. I don't know. You were talking about some Sigma tools. Do you think Six Sigma Bell certifications are valuable for DevOps? Honestly, depends what you're looking for in your life. I don't have any certifications, right? The only certification I have is the driving license for a tractor, so, and to operate a chainsaw, because my former study subject was a forestry, so, but that was very long time ago. And at the faculty of the forestry in the Zvolen University, I become very fond of science and math and statistics. And this is what I took from my university years to my IT profession. What would you use to measure the average request throughput of a service? How do you handle peak time and little to no traffic overnight, etc.? How would you handle peak time and little to no traffic overnight? I don't really understand what you mean by how do you handle peak time and little to no traffic overnight. But how would you measure the average request throughput of a service? I saw the I put a little formula how we can actually measure the average request throughput of a service. So you can take the response time of endpoint, for example, and create a very simple mean average. Which observability tools do you recommend to use? Well, for Kubernetes, the choice is obvious. At least in my opinion, I like to use Prometheus. I like to use Grafana. I used a lot before in the traditional uh, server landscapes. I use a lot of Elk Stack, Elastic, Logstash, and Kibana. And I do a lot of custom tooling development for my customers or for my jobs. But I use the OpenTelemetry as my main stack. Thank you very much.